Okay, so yeah, let me see. Yes, so in this lecture, in last lecture, I think we spent most of time by going through the solution processes of a typical diffusion equation with this set of given boundary and initial conditions. So let me use this for screen. So yeah, so the basic idea is that we use separation of variables, right? So because your concentration profile is a function of both space and time, and let's, we initially say, okay, let's just assume the solution has a particular form that you can separate the contribution from x and t and into two different functions, and this can reduce the initial PDE into two separate ODEs, right? And then we solve those ODEs by try to make them fit both the boundary condition and the initial condition, and eventually we end up with this solution. Okay, so if you look at this solution, I think the physical idea is pretty straightforward. First, you have this spatial term, the sine 4 pi over L times x, that is basically picking up what is the initial fluctuation you have in the system. And in this case, our initial condition is very simple. It only contains a single sine curve. So you just need one B, right? This is B4 to pick up this particular spatial modulation based on your initial condition, right? And on top of the spatial modulation, we have a temporal modulation, which means that, if you focus on each particular point, right? So if you focus on particular x, you can choose x to be pi over 2, for example, or overall this x equals to, I think in this case, 1/4 of L, right? Or 1/8 of L, I'm sorry, 1/8 of L. So you're gonna have pi over 2, which is this point, right? If you focus on the evolution of this point over time, you're gonna have a temporal modulation, which is determined by both diffusivity and this particular, the spatial modulation. So this means that, and overall, this is going to be a decay, right, of the magnitude, because this is an exponential function. This is a monotonic decreasing function of time. So the longer you have, the smaller this value is. And this is a prefactor for all of the concentration profile at any point in the system. So you'll know on average, the fluctuation turns to decay, right? And how fast the fluctuation decay clearly determined by the diffusivity, the kinetics of how fast these particles move around to smooth out the fluctuation, but also it depends on the spatial modulation. It depends on this lambda, right, which determine the spatial modulation of your system. And we'll see some consequence about this, very interesting consequence about this. So that's basically the solution we have for this particular problem. And then we move on to, oh yes, and this is basically, if you were asked to sketch the evolution of the concentration profile, this is what we're gonna see, right? Starting from t equals 0, you have this purple curve, and then as time proceeds, you see that the magnitude of this fluctuation is gonna get smaller and smaller until when t goes to infinity, everything gonna be smoothed out. You're gonna have a straight line. So diffusion generally smooths out density fluctuations, which is quite intuitive because these particles are driven by the concentration gradient. So you want to, the overall process is to reduce the concentration gradient, so it smooths out all the fluctuations. And then we move on to describe some very interesting but to examine, what. So this solution actually encode all information you have for the diffusion equation, right? And we know that diffusion equation contains both Fick's first law and Fick's second law, which are respectively the Fick's law for the flux as well as the continuity equation. So it's very much like that when we have the solution, you have all the information, and how can you now decipher all of the details from this collective set of information, right? How can you, if I give you the solution of the diffusion equation, which is shown here, now how can you go back and find out what are the flux in the system and see whether the solution is consistent with the two Fick's laws, right? This is what we're going to do, because only we do that, we can guarantee or make sure that we do understand the solution, right? Not only see, be able to work out the mathematics of the solution, find this very nice functional form, but really be able to understand what is the physical implication of different parts of the solution. I think this is very important for this class. So that's why we have this example, right? I ask you to, draw some conclusions about the flux in the system, right? And to do so, we know flux is defined through the Fick's first law. right? This is the flux of particular solutes and this diffusivity, and we know that we take the derivative with respect to the concentration profile and take the negative times diffusivity, we get flux, right? And then, it's very straightforward to do that because you already know the mathematical form for the concentration profile. So you just take this guy and differentiate this guy with respect to x, and only this term is relevant because the temporal term does not going to play any role when you do the differentiation with respect to x. And have the Banner sign here, you take some constant out, and you change the sign to cosine, and this is your flux, right? And this flux is defined for all x, okay? So we do the differentiation, and for this general form is the flux for all different x. And I'll ask you to pay attention to what is the spatial modulation for this flux now, okay? So it changed from sine to cosine, okay? Now we're gonna have a question later about this, but for now, let's just examine what are the flux at the two boundaries, right? Because we want to see whether there are any flux at the two boundary. The reason why we want to see that is because we know the conservation is conserved within this domain, right? Now, note that this statement about the conservation is not the statement of the conservation of solutes when we derive Fricke's second law, right? The Fricke's second law is what we call the local conservation of solutes. It's only going to be applied to a very, very tiny volume, a differential volume in the system. So if you basically pick a very small chunk of volume, and you know that all the rate of change, all the change of concentration within this small volume are due to the flux on the two boundaries. In here, we're talking about a much larger domain. We're talking about this conservation of solutes in this entire domain. Yet, you see that within this domain, there's no solutes being created, there's no solutes being destroyed. So the only possible way that how the solutes is going to change, or the amount of the solutes, the change of the amount of solutes are due to flux at the boundary, right? And we also see from the analysis and from the mathematics that within this domain, the solutes are conserved. So we want to check, okay, whether there are any flux at the boundary that are, or if there are flux, are these flux consistent with the overall condition of conservation of solutes? That is what we tried to do in the last lecture. And the most, if I told you that the solutes is conserved in this domain, I think the most intuitive, way to think about the flux will be that there will be no flux at the boundary, right? Because, if you have no atoms in, no atoms out, of course, the number of atoms is conserved. But when we work out, so I just posed this question, and I think this is really a tricky one, because when we work out this flux at the boundary, we do see that it's non-zero, right? You can also see this from the definition of flux, which is proportional to the derivative. And at both ends of this concentration profile, you'll see that as long as t is not going to infinity, the flux will never be zero, right? So there are flux at both ends of the boundary. But how this can reconcile with the fact that the solutes are conserved? Well, because one scenario for the conservation of solutes is that you have no solute, you have no flux at the boundary, and the other is that you have the equal amount of particles flow in one direction and flow out in the other direction. I don't care what's happening within the box, as long as I put in the same amount of atoms as I take them out, as the same amount of atoms I take them out, I still have conservation of total atom within this particular domain. And this is what's happening, right? We have non-zero flux at the boundary of this domain, and the magnitude and direction of the flux is identical, is the same, right? So it looks like, if I don't care what's going on within this domain, it looks like that there's the flux are flushing through the system, so that anyway you still have the conservation of solutes. This is what we discussed in the last lecture. Any questions up to this point? If not, let's move on. Okay, so now I would like to, so for the previous example, we just look at flux at two boundary points, right? So this is just a kind of interesting starting point. But as I mentioned before, when you actually take the concentration profile and employ Fricke's first law, you can obtain the profile for the flux, right, for all different x at any time t, right? So this is not just a flux at any point, it's the flux in the entire domain of the system. So now, if I would ask you to make a sketch of this plot, of a sketch of the flux profile, now what this function looks like? Does the function look like same like the concentration profile, or looks differently? It's going to look something like that, right? apologize for the very unclear labeling, but you get the idea, right? We're just interested in the shape of the function. So this is our domain, right? And because this is a cosine, right? The spatial modulation of this function is a cosine. So we're going to start with this, with the largest value, and go back and forth again. Okay. Now, again, this is just a schematic showing the rough oscillation. You have a negative sign here, so maybe you're going to flip this. But again, just want to show you the oscillation of the flux. So you see that the flux within the system is also not uniform. Okay. And the profile of the flux is different from that of the concentration, right? And do you see any correspondence between the two? So we'll give another example, and hopefully this will help us to appreciate, what's happening. So now let me if you look at this particular profile, okay? Now at what locations there's no flux?
Where the function crosses the x-axis.
Exactly. When the function goes to 0, you have no flux, right? Like this point, and this point, and this point. Okay. So now if I ask you to identify what are the corresponding value for the concentration at these associated points, okay, what do you find? So this is a position where you have no flux, right? Or we can say that the magnitude of the flux has a minimum at these points, right? And now what are the corresponding concentration profile? What are the corresponding concentration value at these associated points? So I can tell you this is pi over 2, this is 3 pi over 2, this is 5 pi over 2, and this is 7 pi over 2. So what are the value for the concentration? This is pi over 2, this is 3 pi over 2, 5 pi over 2, 7 pi over 2, right? So you see that, we have 0 flux, okay? You have local maximum or minimum for the concentration, or the largest fluctuation for the concentration. Does this make sense? Mathematically? Yes, right? Because this concentration is sine profile and flux is cosine profile. So of course, the maximum and minimum, they're complementary to one another for these two functions, right? But physically, does this make sense? Okay, so basically I located these points. So the first time I see this, I think I was a little confused, because if you look at these spots, right, and you have the largest fluctuations here, and when you do the mathematics, we will see that these are not the exact same plot, but the rigorous plot, but you will see that these points are the ones which are going to have the largest rate of change for their concentration. They're going to have the largest possible rate of decreasing or increasing of the fluctuations compared to other points in the system. Does this make sense? So if you look at how fast at this point you can drop to this value over a given time, then this drop is the largest compared to all the other positions, right? And similarly, the increase of this is also the fastest compared to all the other points in the system. But what caused the increase or decrease of the concentration at this point?
The flux on each side, like on the opposite sides, is very different at this point.
Exactly. So that's the point. You see, so this is the point I'm making here, that apparently you see that the flux at these points are 0, right? Have a very minimum, very small flux or no flux at this particular point. Yet the concentration profile has the largest rate of change at this point. Apparently this is kind of a dilemma, right? A conflict. But however, if you carefully, think about this more carefully, it's not the value of the flux. It's not the magnitude of the flux that determine the change of the concentration. It's the difference of the flux, right, along two opposite wall or opposite surface of that small region. Okay, so if you imagine that you can construct a small region here, it's not the flux that right at the center of this highest point that determine how fast my concentration is going to drop. It's actually when you construct a small box, it's the flux on both sides of this box, right, going to determine how fast your concentration profile is going to drop. So this is very important. So we know this seems clear to us when we derive the continuity equation, that we start with that differential box, right? But is this still clear if now we have the whole solution and now try to rationale whether the solution makes sense to us by going back to this differential picture. I think that's a kind of interesting practice. So basically, we see that this already we already went through this together. So the question that I posed that why the places with no flux associated with the fastest change of concentration, right? So the conclusion or the answer for that is that it's not the magnitude of flux that determines the change of concentration, right? It's really the difference, okay, over certain distance that determine the rate of change. And you can actually do this because this is a Fick's second law, which is a conservation equation, right? So it's the difference of the flux over a certain distance associated with the small box that determines how fast your solution is going to change or decrease or increase within this small region. Okay, and in this case, because the flux on both sides of the box are in different directions, because this is going to be a positive derivative, this is going to be a negative derivative, right? So the flux are in different directions. So you have flux that are going to have atoms that are escaping from this small box in this region in both sides. So this basically give you a reason why the concentration at this point is going to decrease or increase. In this case, they're flowing in, right? So give you the fastest rate of change. Okay, so but if you take any other points, for example, right here, okay, if you do the same construction, have a small box here, okay, and you compute the flux along both sides of this box, what are you going to have? What are you going to have? Are the flux in the same direction or different direction? If you have any, like a flux right here,
You would have them in the same direction, right?
they're going to have the same direction, right? So you have some in, but you have roughly the same amount of come out. The difference will just be a little bit, So that's why, although you have the largest flux here, right, around this region, but you get whatever you get in and you get out. So that's why the concentration does not change at this point, although you have the largest flux at this point, at these 3 pi or 2 pi or pi, right? But you have exactly the same flux in this differential volume, so the concentration is going to never change. Okay, so that's a different way of looking at the Fick's law, right? We examine the first law by working out the flux, and now we examine the second law by looking at the concentration profile, and then make sense of how you're going to match the rate of change to the actual local change of flux, which is derivative. And if you think about this, okay, now if you take the derivative again with the flux, this is the flux, right? We already take this. And if you now take the derivative again with this flux, what do you get? You get back to the sine profile, right? So basically you take this cosine with respect to x, you get it back to the sine. And that the maximum value for the sine function is the place where you're going to get maximum change of concentration. So that exactly match what we already obtained from the full solution. Okay, so again, this is just a reinforce of the Fick's law, but this is kind of already we have the solution, and we're gonna examine the solution against the Fick's law and see whether this makes sense, and hopefully this can better help us to understand, from both the differential point of view and this global point of view of what's going on for this particular problem. Okay, did that make sense to everyone? Okay, if that, let's move on. Okay, so I think this is sufficient for the solution of diffusion equation for this particular problem. Now let's look at some more interesting consequences of the solution. Okay, so again, this is what we already analyzed, right? If you have a particular spatial modulation, and we know that we're going to have this decay, okay, of the flux of the concentration at each point via this exponential. And I did mention that the rate of decay, which is determined by this guy, d times this guy, right? That's going to determine how fast you're going to decay. Is of course related to the diffusion coefficient, right? This is an atomic mechanism, how fast atoms can move around, but also is basically associated with the spatial modulation, this 4 pi over L, right? This is your lambda. You can imagine this is kind of a wavelength of the system. So let's see if we apply this solution to two different boundary initial condition, okay? Though the domain is the same, you still have the system defined from 0 and L, right? This is the same domain you have. But in one case, instead of putting 4 of these oscillations, I only put in 2, right? And on the other case, instead of putting in 4, I put in 8. Is that 8 or 6? I can't remember. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I put in 8 oscillations. Now, without actually going through the solution again, now just tell me what the solution is going to look like for these two initial concentration. What the only thing that you need to change? If this is your general solution, suppose I give this in your homework or give this in the exam, and I give these two boundary conditions or initial conditions, and what is the only thing that I have to change in order to get
And-
solution for this
The
guy?
value of n.
The value of
Exactly, right? Because in here, we still have a single modulation mode, right? It's not a very complex combination of different modes. It's still single modulation mode. So for this guy, instead of having n equals to 4, okay, what value of n you should choose?
2.
1.
2,
Two.
right? If you're basically, in this case, number of n is the number of oscillations you have, right? Now, each of this is just correspond to pi. So you have 2 oscillations, you have 2 pi. So n equals to 2. Right? If n equals to 1, you're going to have a single, no oscillation, just a single curve like that. Okay. Now, and for this guy, we counted together. I think we have 8 oscillations, right? So what is the value of n you should choose for this guy?
8.
8, right? Does that make sense, everyone? Is that straightforward? It's just a direct analog for this guy, right? Because you have a single modulation, you just choose the particular wavelength for that modulation, and that is only non-zero Bn in your general solution. Okay. Now, the question for you is that, okay, so now if I want to monitor the decay or the evolution of these two density fluctuations, you can have, this is what I call a very, a slow fluctuation, right? You know, your fluctuation change very slowly with respect to the spatial coordinates, right? And this one I'll call it a fast fluctuation, you know, the density fluctuation change very fast compared to this guy, right? For the same domain. Now, if you have a slow fluctuation versus a fast fluctuation, okay, we know that this is going to give you a different spatial modulation, different n, but which fluctuation going to decay faster? That's the question for you.
The second one will decay faster.
The second one going to decay faster, right? Does this make sense to everyone? It is clear to see why the second one is decaying faster.
Higher value of n.
It's a higher value of n, right? And because we have this exponential form here, because this guy is larger, right? It's a squared, and it have a much larger negative factor that you're in your exponential. So you know that this is going to definitely give you a much faster decay because this is your prefactor, right? Compared to this this is your temporal modulation compared to this, because you have a much faster decay in this factor. So that's why this decay faster. So I'm just briefly illustrate that for you. Again, this is a schematic plot, which is not quite mathematically correct, but you see that suppose after a certain time, for this very, very slow oscillation, we just have a very small decay, right? But for the fast, we already have very fast, large decay. Does this make sense to everyone? I guess so, right?
Yes.
Okay, so now this is one reason we see why this faster oscillation have a faster decay, right? Because I already told you, you should pay attention to this prefactor, right? This lambda here. Can you offer me another solution, a more physical solution, by considering what actually caused the concentration to decay in this system? What is the physical driving force for the fluctuations to smooth out? Generally speaking.
Difference in the
flux, right? Or the derivative of the flux, or the rate of change of the flux, or something like that. In general, if you in a system you see a larger or faster changing of flux, right? This is going to give you a faster decay or faster change of the concentration profile, right? But what determines the flux? The derivative, the concentration, the rate of change of concentration with respect to x, right? Based on the Frick's first law, which I don't have anymore, but let's go back. This is the Frick's first law, right? How fast the concentration profile change with respect to x gonna give you, roughly speaking, the flux, right? So if you have a faster changing concentration profile, this implies what? You're gonna have both larger flux and you're gonna have a larger rate of change for the flux with respect to x. Does that make sense? So this means that if you have a concentration profile like this, if you look at the flux at this point, it's going to be much larger than the flux at this point, right? And if you look at the differential or difference of flux at this point, because you have a huge derivative, right? In this, near this, in the neighbor region of this point, so you're going to have a much larger flux, away from this point. In here, you have a much smooth change of concentration profile. So the flux and the difference in the flux will be much smaller, right? So this is another reason, we don't have to go back to the mathematics, but just think about the physics, because in here you have much larger flux, and the associated rate of change of flux or derivative of the flux with respect to x. So that's why you have a much larger decay of the concentration fluctuations. Does that make sense to everyone?
Yeah, Professor, a quick question.
Yeah, sure.
Is there any chance that you could upload this files? Because in a lecture file that you have on Canvas, this couple of pages are not there.
I think I already have the latest one uploaded. I correct some of the typos, and the PDF that you should see there is already the updated version.
No, I just looked at it, and it's not. It doesn't have this previous page that you showed, and it doesn't have this page.
Okay, I'll double check. and upload. I think I uploaded this last Friday, but I'll double check. Thank you.
Okay, thank you.
I just noticed another typo here. This should be sine 4 pi x. But anyway, that's that, right? So are we clear about this? So what do we learn here? I think I have a conclusion for you here. Is that the fast oscillations typically relax faster, right? Because you have large concentration gradients, you have large flux and flux gradient. So if you have a faster oscillation, a nasty density fluctuation profile, no, don't worry about it. Fluctuations, the diffusion going to do the job to smooth out these faster fluctuations more rapidly. Okay, this is what we learn from the single mode analysis. Now, how about we do this? If I give you a more complex, more random fluctuation profile like this, okay? I just did this random drawing by hand, so don't give too much mathematics about this. But let's try to work out. Okay, if I ask you to make a prediction. Okay, I would never ask you to write down a solution for this because it's not feasible. But based on what we learned, right, from the mathematics, from our understanding of diffusion, I will ask you to make a prediction or a sketch of the concentration profile based on this initial profile after some time t. How would you do that? What is your new concentration profile looks like?
You could do a summation of a lower frequency plus a higher frequency system.
Exactly. So first, the one thing that we would like to mention is that because you have now clearly, this is not a bimodal system, but you see that you have oscillations of different types in the sense of their wavelengths or things like that, right? So you know that this will never be a simple single mode solution. You're going to have a linear combination of different spatial modulation. Does this make sense? Right, so this is the first difference between this guy and all these simple single mode solutions, right? You're going to have multiple modes in your solution, but how much each mode is going to contribute would depend on the detailed mathematics for this function, which will not work out, right? So this basically, how would you work out this? You consider this to be a general function, and then you use inner product, right? You time the basis, and then use inner product to find the value for Bn. In general, if I give you another, well-defined mathematical function, this is the way that how you should work on it. But because we're not solving differential equations for this class, I will not ask you to do that, which is good for both of us. But I will focus on more on your understanding of the physical interpretation of the solution, right? I will not ask you to write down the mathematics, but I can ask you, if I have multiple modes in this particular system, right? Which mode is going to decay faster? And which mode is going to decay slower, and after some time, how this concentration profile looks like. So now let's look at these guys, right? These what are called the fast modes compared to these two big guys, right? So do you think that if I allow the system to evolve, do you think that these guys gonna relax faster than these two guys, or they're gonna relax slower?
They will relax faster.
They relax faster, right? Because these guys are pretty much like, I'm sorry. These guys are pretty much like these guys, right? So for the same amount of time, they're gonna relax much faster because of their much larger wavelengths, much larger n associated with them, right? And these guys gonna relax slower. So, but after a certain time, what would you see? you would see that, you know, these faster fluctuations, they're more effectively and more fastly smoothed out compared to these slow oscillations, right? So everything is, you know, kind of smoothed out in a very nice way, because in here you don't like these because they're so nasty, they're very fast fluctuations, but they're relaxing very, very fast. So after some time, you know, you didn't see a lot of you know, relaxing for these two guys, but you know, you may see a lot of you know, relaxing for these guys, and almost they have a overall smooth profile, you know, and this is kind of a deep guy, and then you have a concentration profile like this. Does this make sense to everyone? Again, I do not want you to do a very rigorous, you know, solution to this, but just to be able to demonstrate when you have a hybrid mode, you know, case where you have a combination of both fast and smaller and slower fluctuations. We know the fast mode is going to relax much faster, and then this is going to change how the overall profile looks like, right? You will not see, you know, if you follow simple this line of thinking, you may imagine that I just have the same shape of the curve over time, and everything just gets smaller for the same magnitude, but it's not the case, right? We have a mixture of different modes. These fast modes decay much faster, and they can become flat much quicker than these slower modes. So that's what you typically see for a actual evolution of the concentration profile or concentration fluctuations. Okay, so I think that's pretty much all I want to say about these. Let me see. Yeah, so basically the final conclusion is, again, which already I think mentioned a little bit, is that diffusion homogenizes density fluctuations, right? So if you initially have some density fluctuation and allow the system to relax under diffusion, and after some time, you'll see that the system can get quite homogeneous. And this is typically how people, the way how people use diffusion, you know, to treat materials, right? Initially, you have some carbon, if not quite uniformly distributed in the system. What they do is that they take that, you know, typically a metal bar or iron bar with carbon atoms, and then they heat up the systems to increase diffusion, because we know diffusion coefficient, this diffusivity depends sensitively on temperature. So the keep that bar at elevated temperature, so to accelerate the diffusion, and after some time you'll see that you get quite a, you know, a very nice and almost homogeneous profile for the carbon in your system, which is going to improve the mechanical property. So I think that's all I want to say about this particular example. Again, we introduced the diffusion equation and solution of diffusion equation via separation of variables in the context of this homogenization problem. Okay, so any questions before we switch gear? Okay, if not, let's switch gears. Okay, so so in the previous problem, you see that a very nice thing that we did is we're solving this problem for a finite domain, right? So we solve this for fixed bar of fixed length, and we assume that we have a very nice, you know, periodic modulation for the density profile, for the concentration profile, and this allows us to, in particular, the you know, the boundary conditions and the fact that we have a finite domain allows us to nicely use the assumption for the separation of variables, right? And this basically means that, okay, the solution does have this particular form that you can write down the temporal contribution and a spatial contribution as two different functions. But there are other cases which, you know, there are much more other cases in which the separation of variable assumption is not right, okay? Now in here, I will introduce this in a bit more mathematical way, but it's particularly the same system. Okay, I just want to give you another way of looking at this, because probably the equation, the diffusion equation you will see gonna look pretty much like these. But nonetheless, you know, it's the same thing, okay? So one thing that this is, you know, another way of writing diffusion equation. Again, you know, this phi is nothing more than the concentration profile we have used as C, right? And they have a rate change of this guy, and D is diffusivity, and this lambda, I don't know what's the best way to call this. Sometimes we call this lambda, I guess. This triangle, this down triangle, is simply a fancy symbol for spatial derivative, but it can actually be generalized to higher dimensions, and in higher dimensions we call this gradient. Okay, this gradient operator, and the second order of this guy is, like, in one dimension is just the second order derivative with respect to x. Okay, and this is your concentration profile. Okay, now instead of, so this is basically tells you that we can have this for a high dimensional space, but R is basically, in our domain, right, this is just 1D, so n equals to 1, but we can have n equals to 2 or 3 as well for higher dimensions. And this means that the system is defined in this particular domain. So instead of having a finite length, we are considering that the bar is very, very long, okay? Now, this is mathematically quite understandable. And in reality, this is also reasonable as long as the length of the bar is much larger than the typical diffusion distance for the particular solutes you have, right? So if, for example, if the bar is, 3 meters long, and if looking at carbon diffusion at normal temperature, like room temperature, you can consider bar effectively infinitely long compared to a single carbon atom. So this is quite reasonable. And the initial condition is similar. We just, for all the value of x, including 0, okay? So this initial condition is given as a general function of fx, right? But the boundary condition, which is different from what we discussed before, is that now we consider that this is an infinitely long bar, okay? And instead of considering we have finite length and 2 endpoints, we consider the boundary condition at, the very, very far end in the system, which when x goes to infinity, right? This is conceptually the same thing, but mathematically it's quite different. Okay, instead of having a finite length of the solution domain, now our solution domain is infinite long, but we still require that at the 2, far end of our solution domain, we have no concentration. Okay, so this is what this means. So basically, this is the same type of, similar type of description for the same problem, except for the definition of the domain and the different way that you're writing the mathematics. Okay. Again, I think it's useful to introduce this to you as well, because I think you will eventually see something like that in your, in some literature or some other classes. But anyway, this is just no more than what we described before, but in a different way of presenting them. So now the key thing here is that you see we also have homogeneous boundary condition, but now this boundary is at the infinity, right? This is at the far end of the domain. So now in this case, do you think that we can still apply the separation of variables in this case and get a reasonable solution?
No.
No, right? Because the reason why we get this reasonable solution is because we know I have a sine function, right? Eventually, if you still remember, I require the sine function goes to 0 or at the end of a finite domain has to be 0. And this allows us to select a certain spatial modulation, right? But now if you do not have a finite domain and you have an infinite domain, how would you select your spatial modulation? Because sine function is not quite well defined when x goes to infinity, right? It's keep on oscillating. If you do not definitively know where you're going to stop, what is the length of the domain, you can never say anything, definitive about the value of the sine function you have. Does this make sense to everyone? That is the fundamental reason why the separation variable does not gonna work in this particular problem, because you can also assume that's the case, but you will never find a feasible solution satisfying this new boundary condition. Okay, so that's I wouldn't go through this, and if you're interested and do not trust me, you can certainly go ahead and try that, and this is what you will find. Okay, so when we have this problem, again, the first and natural thing to do is to try what we already know, and we know separation variables, but after we tried this, separation variables do not seem to be working. So this means that we have to introduce a new way of solving this equation. Okay, and that is the so-called Green's function method. And I'm warning you that the subsequent content is a little bit more mathematical, but I will try my best to explain this in a way that at least it sounds physical and makes sense. Again, we do not have to understand each particular step involved in deriving these. More importantly, we need to understand what are the general procedure, why people are doing this, and how, what benefits I can get by doing this. I think that's more important for now. Okay, so the idea is that, okay, so this equation is difficult to solve. Again, it's a differential equation, right? It's a partial differential equation. And I don't know how to solve a partial differential equation. So now in the case of separation of variable, what we did, if we assume the solution have this form, but what is the benefits we get by assuming the solution have this particular form of separation variable? We still remember? we reduce the partial differential equation to what?
Two
A
ordinary differential
system,
equation.
a system of two differential equations.
The system of two ordinary differential equations, right? And we know how to solve ordinary differential equation. That makes sense, everyone? So that's the step. In here, we are using the very same logic, right? We don't know how to solve this partial differential equation, especially if your spatial domain is high dimensional, is higher than 1 dimension, and you have a very, nasty, I would not say really nasty, but, apparently nasty, this, Laplacian or second order of spatial gradient associated with that, which is this guy. It's very difficult to solve, right? So the first thing I want to do is that I want to reduce this guy, this partial differential equation, to ordinary differential equation, right? To some ordinary differential equation that I know how to solve, right? But in here, I cannot use the trick that I use anymore for the separation variables. So in here, I introduced a new trick, okay? Probably this trick is less familiar, but I use the so-called Fourier transform with respect to the spatial variables, okay? So again, I wouldn't be able to derive all the mathematics for you, but I believe at this stage, we should have seen Fourier transform and is some of its applications. Okay, this might be a while since you have seen this, but if you're not familiar with this anymore, I would probably suggest that you do a very quick Google search and you will find a very nice wiki page that summarize all of the essentials for Fourier transform. Okay, but a key property of Fourier transform is that if you take the Fourier transform with respect to the spatial variable, okay, and the differential operator with respect to the spatial variable now become an algebraic operator. Okay, so that this makes sense, or it does not make sense at all? Does this ring a bell, or?
I think so.
Okay,
Yeah.
so let me quickly write down what is Fourier transform. Sorry, I should have this for you. I think I had that for you, but for some reason. Yeah, again, this is not a rigorous mathematics, but typically we use a bar to denote the Fourier transform. And the Fourier transform is basically you take the original function of fx, right? And then you have this guy. My I is an imaginary unit, k is the wave vector, and x is that, and you do this. So basically you do a convolution with respect to this guy, okay? And it's very straightforward to show that now if you, this is a Fourier transform, okay? If you do the Fourier transform, this is what you get. And then it's very easy to show that if you have a second order derivative, right? You have this within the Fourier transform. Instead of taking Fourier transform from x, if you take the Fourier transform of this guy, and you do the differentiation, integration by parts, okay, which I want to show you for that. So if you do, differential by parts, right? So this you integrate this part first, and then the differential operator can apply to this guy, okay? And then at some boundary conditions, things cancel out, and roughly speaking, the differential operator will come out as a algebraic operator on the Fourier transform. Okay, so this is what you have. Okay, so for this guy, because now you do the second order derivative, so you have twice of this k come out. Okay, so that's why you have this. Okay, again, this is a very rough recap of Fourier transform. Okay, I wouldn't have time to really go through all of this in detail, but I just want to quickly mention the trick here. Okay, so now what we want to use is that, again, we want to convert this partial differential equation into ordinary differential equation, right? So this means that I have two derivatives, either with respect to time or with respect to the spatial coordinates. I have to get rid of one of these, derivatives. So to make the equation to be an ordinary differential equation, which is just about one differentiation, not about two variables, right? And because the spatial coordinates are much more complex, involves into a gradient and also on the second order, so it's very natural that I get rid of the spatial differentiation, and I keep the time differentiation, which is very easy to solve, right? So that's why I take the Fourier transform with respect to the spatial coordinates, okay? And then I convert this second order, a gradient operator into a simple second order algebraic operator. So, and then the consequence for this is that I transform the function that I want to solve from the phi xt to what? To the Fourier transform of phi with respect to the spatial variable of this phi bar of phi tilde kt. Okay, so now instead of solving the real space density profile, I'm solving the Fourier component for this profile. That makes sense to everyone? Okay, so if you think about it, okay, in here, essentially we're still working in the Fourier space. And this is the analog of why we're using the sine and cosine analysis in our previous case, right? So if you think about what are sine and cosine, we're also working in the Fourier space, but in those cases, we have a discrete set of Fourier bases that we can directly work with. In here, because of the definition of the domain is infinity, is going to infinity, we cannot have those definitive Fourier bases. So we have to implicitly work with the Fourier formulation for this problem. Okay, so that's the logic behind everything. So in this sense, this Green's function method using Fourier transform is just a generalization of the separation variable. Okay, or you can say the separation variable is just a special case for this analysis. Okay, in the case, let's go on. I hope this is clear. But if you have any doubts, just let me know. Okay. Anyway, so again, the one thing that I'm introducing this is now to ask you to use this to really solve any complex diffusion problem. I just want to introduce this method so you know that there's a convenient way for us to understand another important real application. Okay, and you know, yeah. So don't worry too much if that's not quite clear to you. Anyway, so yes, so this is, you know, our transformed equation, right? Again, this equation is good because forget about all of these things. And this equation is only about time t, right? So we have a function of time t, which is, you know, a constant times this function. So this is very, very straightforward first order differential equation in terms of a function with respect to t, right? So everyone know how to solve this equation. It's very straightforward. It looks complicated, but you know, most of the things like d and k square here are all constant, right? So yeah, let me write down that for you. So basically, if you have a function, right, a g as a function of t, so this is what we have. It simply equals to a g, nothing more than this. And we know how to solve this, right? This is very straightforward. And for the initial condition, right? So again, in here, this is your initial condition. This is for time t. This is for the spatial domain, okay? But now, because we're working with the Fourier transform, so you have to, you know, apply Fourier transform to this initial condition again, and to transform this to be f tilde k. Okay, so now everything going to be consistent. Okay, so I have a differential equation in this form. I have the initial condition. Now I can easily solve this, right? So it's very straightforward to go ahead and solve this auxiliary differential equation, and we have this formal solution, right? You see that this is just exponential, and this d minus d k square or k, you know, absolute value squared in case of higher dimensional case is simply the constant you have here, right? And then this is your initial condition. How you know this? Well, you said t goes to 0, and you see that your solution converts to this guy. So it's very straightforward. So it's very simple to get a solution. Okay. And that pretty much already solved the problem, right? Because you know the initial solution, okay, and you now solve this a problem using the k-space thing, right? And you have this. Now the next time, the thing we need to do is that we have to convert this guy back to the real space, right? And check, okay, whether the boundary condition can be satisfied. That's what we're gonna do next, right? But basically, up to this stage, you already have a solution, a very nice solution in the Fourier form. Okay, so now we take the inverse Fourier transform of this this Gaussian basically, right? But this Gaussian is with respect to both t and d. If you just look at t, okay, this is not a Gaussian. This is a simple exponential decay. But if you look at this function with respect to k, this is going to be a Gaussian. And here you have another function of k. So it's like a function with a Gaussian kernel. And if you take the inverse Fourier transform, again, there's you know, well-defined equations for this. You can derive this by yourself, but it's kind of straightforward. You're gonna get this guy. Okay, so this is when you take the inverse. This is just the Gaussian. I think I need to take this part. You just take the Gaussian, okay, and you get this form. So I use this operator to denote the inverse Fourier transform of this Gaussian. Okay, and again, you know, you take this back into the integral form. You do the integration by parts. And you, you know, at the boundary, because when the k goes to infinity on both ends are 0, so eventually you're going to end up with this guy. Okay, and you can already see, because this is not an inverse transform of the full solution, just this Gaussian part. You already see that you can never solve this by a separation variable, right? Because you see that you have an exponential function simultaneously involve both x, your spatial coordinate, and your time, right? So this part is time alone, right? But within this exponential function, you see both x and t that occurring as the argument for this function. And there's no way for you to further separate this function into two different functions of t and x alone, right? So that's basically another evidence that why the separation variable does not work here. Okay, now this is just the Gauss, the inverse Fourier transform of the Gaussian, right? And we still have to deal with this term. So the way how we do this is that when we have the product in the Fourier space, okay, and when you convert this to real space, the product necessarily reduces to a convolution, or I'm not say reduce, become a convolution. Okay, again, this is one of the properties for the Fourier transform. So we already did the Gaussian core, right? So now we can directly write down the Fourier transform of this product in the Fourier space directly in forms of the convolution. Now, because this time-dependent factor does not have anything to do with x, so it's not going to be within the integral, where the integral is only for the spatial coordinates. Okay, again, n is here is the spatial dimensionality, and for simplicity, you can consider n equals to 1. This reduces to our one-dimensional problem. Okay, so we introduce the convolution. Okay, this is yx fy. This is just the initial condition that you have. Okay, and this initial condition is constantly convoluted with this guy. Okay, this basically, I will show this later. This Gaussian simply tells you that, okay, if I have some particular solutes at one location, over time, how this particular constant solutes spread out over time as a function of time, and how at a particular distance, how this particular solute spread out. And then if you have at any point a different value for this particular concentration, and overall profile going to be a summation or a combination of the spread out effect for all of these initial concentration at different points. Okay, so that's what's the meaning for this convolution is basically that. Okay, hopefully we'll see an example later that can make it clear. Okay, so that's basically offer you a general solution for this this a little bit more complex problem with an infinitely large domain. Okay, so the idea is that, okay, so we use this, and this is what we call the Green's function, this core. Okay, this SNXT, which is this particular form, is the so-called Green's function. Okay, so what does Green's function do? The Green's function again tells you that if I have some constant unit concentration, initial concentration at some point, right? Now this Green's function tells you how this concentration spread out over time at different location. I do think I have a plot for you. Let me show this later. Okay, and then if you have a different concentration at different positions, right? The evolution is going to be independent. You can imagine that you can separate these concentration at different locations, and each one of them going to have their own way of spreading out, and the overall evolution going to be sum over all of this different spreading out. That is what this physical meaning of this guy. Okay, so hopefully I'm not losing you. Now let's look at some example. I think we'll make this clear. Okay, so now this is a particular example that of relevance to our discussion. Okay, and this is actually a method that people use to carbonize a metal bar. Okay, so the way how they do that is that suppose I have a very long metal bar, right, and I want to have some carbon that penetrating this, just this metal bar. So the way that how they do that is the first to cut the bar in half, and then to deposit a layer, a very thin layer of carbon. This is supposed to be C, okay, carbon, at the cross section, and then the glue the bar back. By gluing, I simply mean you're adding temperature, and so that locally these two parts still meet together, and then you basically impose one layer of carbon right in the middle of this bar. And what you do now is that you put this bar, anneal this bar, put this in an elevated temperature, and we know that at this temperature, the carbon is going to penetrate in both directions. right? The carbon atom going to diffuse around starting from this initial profile, and they're going to penetrate in this direction and penetrate in this direction, right? And over some time, you can establish a concentration of carbon distribution in the bar. This is what we call the carbonization processes. Okay, so now we're going to use what we just obtained to try to solve this problem. I think it's very, very straightforward to go ahead. So again, so in this case, if you mathematically look at what is our initial condition, right? Because in this case, we can consider that compared to the initial thickness layer thickness of the carbon, the bar is very, very long, right? They can be considered as infinitely long. And clearly we keep that this end and this end carbon free, right? So there's no carbon on these two ends, so they satisfy this boundary condition, right? And how we should write down our initial condition. Now, if you look at the profile of this carbon concentration, right? So, and you go from this end all the way to here, everything is zero, right? Because initially there's no carbon here, and then everything is zero on this side as well. But there's a huge non-zero concentration as you right across this very thin layer of cross section, right? So, and to describe that very large amount of carbon concentrated at virtually a single point, right? Compared to the full length of the bar, we introduce so-called Dirac delta function, which is this delta x, right? So this function is only non-zero at x equals to 0. Suppose that we set our coordination system and make our 0 right here. Now this function is only non-zero when x equals to 0, okay? And it's 0 everywhere. And when x equals to 0, this guy, intuitively it goes to infinity. But the integration of this this delta x, okay, over the entire domain or just over the cross section give you a finite value. So basically what this means that, if you just do integration over the entire domain, so from minus infinity to infinity of this this guy phi, and this is my delta because it's one dimensional, so n equals to 1 x dx. Okay, so you're gonna get phi naught. Okay, so the integration of this function is well defined. It's equals to 1. Okay, if you include this particular point where it's defined. So if you plot this delta function, it can look something like this. Okay, so it's 0 everywhere except for x equals to 0. And when x equals 0, okay, this guy goes to infinity. But when you do integration of this guy, you get a well-behaved value. Okay, so again, this is I want to go through the definition of this delta function. Okay, but it can be defined in a way in a limiting process. You can consider initially start with a little bit broad distribution, right, and make sure you have a finite thickness, narrower and narrower, but a fixed area, right? And in the limit that the thickness is literally 0, okay, but you still have a finite area, but the thickness is 0, and you get a delta function. Okay, this is how the delta function is defined. But anyway, this is the mathematically a convenient way to describe this particular situation for the carbonization problem. Okay, and this is our initial condition. So now what we're going to do is that we're going to apply the Green's function method to this initial concentration profile. Okay, and see what we're going to get. Okay, so in this case, the concentration again is only non-zero at this particular location. So we're only going to get effects at this location, right? So basically this means that initially I have the carbon right here, and the carbon going to spread out, okay, gradually and influence and penetrate more and more further from their initial condition, right? This is the intuitive idea of what's happening here, and we're going to see this from mathematics. So so formally what we do is that we plug this equation, this fx equals phi naught, and this delta function in the convolution. Okay, and we know that due to the nature of the delta function, right, it's only non-zero when x equals 0. So what we do here is that we plug in, this is going to be y here. So we know that this integration is all 0 except for y equals 0, right? And when y equals 0, we simply get exponential x squared over 4 dt, and this is going to out of the integration. Okay, so it's very simple. Yes, so you basically plug this into the Green's function, right? And you have phi naught right here because it's a constant. So and when you actually do the integration and evaluate this at y equals 0, you simply have this term. Okay, so, and this is our solution. Okay, and you can easily check that this satisfies both the initial condition and the boundary condition. And I think for the boundary condition is pretty straightforward. You've said x goes to 0. Okay, for all t, you'll see that this is exponential, right? It's a Gaussian type of decay, and we know when x equals 0, of course, the value of the concentration of the boundary is going to equal 0. Okay, the initial condition a little bit tricky because at t equals 0, see this guy is diverging, so you're going to eventually recover this. Okay, but it's a little bit tricky, but it's fine because we derive this solution from the initial condition, so we know that it definitely satisfies that. And also we can see it's consistent. Okay, so now in order for us to understand this a little better, let's look at again what this concentration profile looks like at different time t, right? So clearly, first you see that again this is our solution, and it's quite clear that why this solution cannot be written as a separation variable type of solution, because the t and x, they're intrinsically coupled together within this exponential function, right here. So you can never write down this as a separation variable type of solution. Then how the solution gonna looks like? Okay, so this is, again, a very rough plot of the solution. And of course, it's definitely not to the extent where we should show the infinity. It's just the local field, okay? But this is going to give you an idea. Okay, so the sequence of the solution is A, B, C, D, and E, okay? So initially, we start with this phi naught, okay, which I cannot show because it's going to be a very highly peaked infinite function. Is the height is very, very, very high, which I cannot show on the plot. So what I'm showing here is that this is this purple curve is the profile after some initial evolution. Okay, so you see that still is quite narrow. Okay, so physically this means that the carbon only penetrate a little bit in the surrounding region. Okay, and you can basically assign the size of the region to be within, for example, the first sigma of this Gaussian, right? Because this is essentially a Gaussian, so you can define a sigma. Okay, and this basically the distance for the penetration is roughly here. And if you allow the system to further evolve, you know that the carbon going to penetrate more to both sides of this bar. Okay, and from the mathematical point, well, this means that the distribution going to become a little bit wider. Okay, so that's come to the blue curve, right? You see that now the height right here gets lower. This means that more carbon escape from this high concentration region, penetrate into the surrounding regions, and the penetration going to get thicker because you see the region of penetration get wider. Okay, and this simply goes on. So if you wait a little bit longer, you see a further decay of the concentration within this middle region, and then the carbons diffuse further and further, and then eventually the red line is the later time that you have almost is a relatively smooth distribution of carbon. Okay, of course, when t goes to infinity, you're going to have the carbon going to be uniformly distributed within the bar, right? But typically, we wouldn't be able to wait that long time for real engineering applications, but we'll wait for sufficient long time and increase temperature a lot, so the carbon penetration is going to be very fast. Okay, eventually we won't get a very uniform distribution, but a more or less uniform distribution based on these processes. Okay, so that's basically for this particular one. Okay, there's one more thing I want to draw your attention. Okay, so I mentioned that essentially we can consider the penetration distance to be this, right? So suppose that we have a Gaussian. Let's focus on the purple one, right? This is kind of corresponding to an early time of the penetration processes. Initially we have everything concentrated at this single point, right? And after some time, we know that the carbon diffuse a little bit around, right? And this is a Gaussian, so we know from statistics that the distance of this guy is roughly 2 sigma, right? Where sigma is the standard deviation. Does this make sense to everyone?
Yes.
Okay, so now my question for you is that, okay, so the sigma is also roughly, tells you the distance, how far the carbon has diffused, right? Now I want you to compare okay, to this equation, to the solution, and tells me that what is a rough expression for sigma you have. Again, sigma is the distance, right, of how far the carbon has penetrated through diffusion. Now, if you compare this to the equation, what is your sigma, roughly speaking? We don't have to make precise.
Is it the term in the exponential?
Is the term in the exponential? Yes, but exactly what this term is? Does that make sense? So your sigma square, I think this is 2 sigma square equals to this, right? So there's some constant, but let's just focus on the scaling. Your sigma square is dt, right? So what is your sigma?
Square root of dt?
Does this look familiar? Does the square root of dt looks familiar?
Yes.
Yes, yes.
Yeah, this is what we typically call diffusion distance, right? So this is the distance of a diffusing particle travels on average, with diffusivity over time t. Right? Does that make sense to everyone? This is, I think, from I don't know, from a chemical engineering or typical thermodynamics class where you do diffusion of liquid state. We introduced this also in the beginning of the last 2 lectures ago, I guess. This is what typically we call the diffusion distance, right? It's a distance traveled by a diffusing particle associated with diffusivity and over time t, right? And you see clearly that this distance is manifested in our problem because how far the carbon atoms can penetrate into both sides of this metal bar is basically due to diffusivity, right? It's due to diffusivity, so that penetration distance or penetration width gonna be proportional to this quantity, which is basically square root of dt. Does that make sense to everyone? So yeah, so basically this is a solution. We have went through all the trouble to get the solution, but you see that it encodes a very useful rule of thumb that we already know, right? So in most engineering applications, people do not go back to this full solution. They just work with dt and square root of dt, right? If you have a bar of certain length and they basically know the diffusivity and they use this number to estimate how long you need to keep this bar, at this elevated temperature, so that roughly speaking, the carbon can penetrate, the whole bar or things like that. This is how they use this. Okay, but of course you see another decaying factor. Except besides this exponential decay, you have another decay associated with the temporal decay as well. Okay, so this basically characterize the this basically characterizes the decay of the width, the spread of the concentration profile, and this temporal decay, this factor characterize how the temporal decay of the highest magnitude right here. Okay, this, you look at this is like a prefactor that we had before, right? But in here, simply because these two are more intrinsically coupled with one another. Okay, so that's I think that's for this particular problem. Okay, let's move on. Again, this is, we introduced the Green's function method because I think it's useful and in particular quite helpful for us to solve this problem and understand, why we have each of these different terms and where they come from, right? Things like that. But again, in this class, I will never ask you to solve an equation using Green's function. Okay, the only thing I'm asking you is to be able to appreciate this particular solution, understand where it comes from, and then be able to associate it with the solution with the physical understanding of, physically what's going on, what is the penetration distance and how this is consistent with our normal understanding of diffusion distance, etc. Okay, that's the only thing I want from you for this. But I think for me, I think it's fair to go through all of the solution processes so I can show you that where the solution comes from. And hopefully in future, if you have any chance to work with Green's function, you're going to ring a bell that what that is. Okay, so, and that is all I want to say for this slide. I think I have one more or two more slides for you. Okay, so before I move on, any questions on this? Okay, hopefully I'm no questions because I hope it's not because I lose all of you. Anyway, so let's move on. Okay, so up to this point, I think we have a good picture of diffusion right now, right? So we start from a very simple mechanism of solid state diffusion, which is interstitial diffusion, right? We go from there and showed that we can easily, from a very simple physical consideration of random hopping of atoms, to derive the Fick's first law and associated important physics to the diffusivity in the solid state, right? And then we move on to work with the continuity equation to derive the Fick's second law, and we combine these two together to have the diffusion equation, right? And we spend 2 lectures solving the diffusion equation, under different conditions in different cases. We're introducing 2 methods of solving them. Both of them are very, very, useful in different situations, and we were able to understand the solution, right, and be able to associate, physical meanings for the solution back and forth. Which is, I think, is a great achievement. Now let's move on, because up to all this point, what we have been discussing are based on the Fick's laws derived for interstitial diffusion, if you remember. And the examples we have also for interstitial diffusion, because we use carbon in steel, right, in iron. But how about other type of diffusion? How about other mechanisms in solid state associated with diffusion? Would this change any mathematical descriptions, or would this change any physics, right? Or, in particular through the diffusivity? And this is what we're trying to understand for, I think, the rest of 5 minutes or 3 minutes, or I think I will probably reserve most of this for the next lecture, but I do want to briefly start this. Okay, so that's the motivation for this discussion. And if you think about, what are other possible things that can diffuse around in a solid state, okay? We talk about interstitials, which is quite natural, that, there are many alloys that are of this type. And the other, I would say most commonly seen diffusion will be either called self-diffusion or substitutional diffusion, right? Now, in this case, in the interstitial diffusion, what you have is that you have these atoms that are sitting in the interstitials, and they move around, they hop into nearby sites, right, by squeezing through a densely packed pair of the parent atom in the parent lattice. But for the substitutional diffusion, is that you have some atom right in the lattice, right, and there's a vacancy nearby this atom, and when this atom hop into this nearby vacancy, we have a diffusion occurring, right? And this red atom is again highlighted not because it's a different atom, it's simply because this is the atom going to be moving, right? So you can have self-diffusion if everything is, this random atom is the same type of the rest of the atoms. This is called a self-diffusion. Now, if this red atom is a different type, for example, if this is aluminum, or the other is a copper, this is called a substitutional diffusion. But you see the physical mechanism is the same, right? So I think that's all I want to introduce, given the limited time. But after I introduce the example, I want to ask you this question. So hopefully to get you back from the damage of the previous few slides. So now we see now this shows the way how you're going to have self-diffusion or substitutional diffusion by hopping into a nearby vacancy site, right? Now my question for you is that, suppose we have a perfect crystal, it can be very small, nano-sized crystal, but a perfect crystal in which we have no defects at all, okay? A perfect crystal, say aluminum, where we have no defects at all, right? It can be of small size on a nanoscale, so you can make sure there's no defects. What will be the diffusivity for the aluminum in this small crystal at any temperature? I'll say at below melting temperature. What would be the diffusivity? Is this a clear question?
Would it be constant?
It's a constant, yeah. At a given temperature, it's a constant. So another way of asking this question, that what is the condition for you to have self-diffusion? We know interstitial diffusion is straightforward, right? So, but there's a hidden condition here, which I already illustrate.
Oh, you need vacancies?
You need a vacancy, right? If there's no vacancy, all the atoms just get stuck in their position and there's no diffusion going to occur. So if you have a perfect defect-free crystal of any atom or any metal or whatever you want, your favorite material, what's going to be the diffusivity?
0.
0, ideally 0, right? There are some other issues, you may have, very strong radiations knock one of the atom out, but that's a different thing. Suppose that we just have, in the ideal case. So, this is one difference between self-diffusion and interstitial diffusion, right? Interstitial diffusion can just occur on its own because typically we just add a very small amount of solutes. So there are a lot of available sites for them to move around. And in particular, in our derivation of the Fick's laws, we assume that we have very low concentration. So these solutes are just move in a kind of independent and random fashion, right? This is when we derive the Fick's law. But in here, you see, it's not true. For self-diffusion, if I have no vacancy, there's no way for me to diffuse. Okay, so, the diffusion of the actual material particle, material atom, and the vacancy, which I didn't show, they're actually complementary to one another, and it's actually the same process, right? We can say this atom is diffusing, or we can effectively say this vacancy is diffusing around in a system, right? These two processes, it's two different ways of looking at the same processes. But the key I just want to introduce here is that, vacancy is crucial for self-diffusion or substitutional diffusion, okay? And we will see that there's a physical consequence how this come into the picture of diffusivity, okay? So for the sake of time, I'll just stop here. Yes, I'll stop here. Let me stop recording.